I could have just made section 3.2 part of 3.1 because the concepts are basically the same. The big things we're going to do in this section are determine if y is a function of x and find the domains and ranges of functions. The difference between sections 3.1 and 3.2, in section 3.1 the functions only had a handful of points. There were finite functions. And in section 3.2, we're going to be dealing with functions that have infinitely many points. They're infinite functions, and the processes of answering the questions are different. So I just made it into a different section. So the first thing we're going to need to be able to do in this section 3.2 is if I give you a graph where the points are connected. When the points are connected in the graph has infinitely many points. If I give you a graph when the points are connected, how do I determine if y is a function of x or y is not a function of x? Super easy to do. We just do something called the vertical line test. If I'm given a graph and I'm asked to determine if y is a function of x, if it's possible to draw a vertical line can be drawn to touch the graph of the function in more than one place, then y is not a function of x. So rather than looking for 2 points that have the same x value, if I'm given a graph of a function and I want to determine whether y is a function of x or y isn't a function of x, I do the vertical line test. If it's not possible to draw a vertical line anywhere to touch the graph of the function in more than one place, then y is a function of x. If it's possible even only in one place to draw a vertical line to touch the graph of the function in more than one place, then y is not a function of x. And I wrote an example here. Here I have a parabola on its side, and I want to use the vertical line test to determine if y is a function of x or not. And I took the time to label some points. Here, it is possible to draw many different vertical lines that touch the graph in more than one place. This vertical line that I drew touched the graph twice. Immediately, if you can draw a vertical line to touch the graph in more than one place, the answer to the question of whether y is a function of x or not is y is not a function of x. There are hundreds of vertical lines I probably could draw here to touch the graph in more than one place. Just one possible, if there's any lines that can be drawn that are vertical, that are parallel to the y-axis, that touch the graph in more than one place, it makes the relation not a function. And why is that? Because this vertical line that I drew, it goes through the points 4, 2 and 4, -2. Any place where my vertical line touches the graph is one of the points on the relation. Here, this vertical line's found 2 different points on the relation, the point 4, 2 and the point 4, -2, because it crosses the graph at those points. Anytime I draw a line, any place where the line intersects the graph, that's a point of the function or a point of the relation if it's not a function. These 2 points have the same x, so y is not a function of x. I don't need to know what the points are. If I drew this vertical line touches the parabola on its side in 2 places. That's enough for me to know that y is not a function of x. If I simplified this graph and I ask you the same question, does this graph represent y as a function of x? Well, I have to imagine every possible vertical line that can be drawn through this graph. If there's no possible vertical line that can be drawn that can touch the graph in more than one place, then y is a function of x. And over here I drew some of those vertical lines. Here's one vertical line, only touches the graph once. Here's another vertical line, only touches the graph once. A third vertical line only touches the graph once. I don't see it possible to draw a vertical line to touch the graph in more than one place, and that makes y is a function of x. Or we can just say this is a graph of a function. You're going to need your graphing calculator in a bit, so make sure to have it handy. So the first 10 problems just give me graphs and ask me just to use the vertical line test to determine if y is a function of x. I don't have to draw any vertical lines in, but I can. Problem 2, my answer for each of the first 10 questions is either going to be y is a function of x or y is not a function of x. And that has to do with if it's possible to draw vertical lines to touch the graph in more than one place. Problem 2, I'm going to write y is not a function of x because I was able to draw a vertical line to touch the graph in more than one place. For problem 4, I don't think it's possible to draw a vertical line to touch the graph in one place. I've drawn 4 vertical lines, and each of them only intersects the parabola once. And I don't think I can draw, I could probably draw 100 more, and if they're truly vertical, they aren't going to touch the graph. They're only going to touch the graph once. So for number 4, the proper answer would be to say y is a function of x. Quite honestly, if I was writing up a test key, I would probably write this on my test key rather than writing the whole verbiage. That's the lazy way to say something that most mathematicians would understand has the same meaning. No algebra again, so many problems in this chapter that are algebra free makes it hard to give partial credit. For 6, same question, is y a function of x? Well, let me draw this vertical line right here. This vertical line touches the graph in more than one place. It doesn't have to be that every vertical line can touch the graph in more than one place. If there's at least one vertical line that can be drawn to touch the graph in more than one place, then we have to say y is not a function of x. Or just not a function. And then for number 8, that's not even a vertical line, but it's as vertical as I'm going to get right now. Doesn't really matter. I don't have to draw any vertical lines. I just have to visualize every vertical line that can be drawn. And the semi-vertical lines that I just drew, they only touch the graph in one place. So I'm going to say y is a function of x. Similarly, for number 10, it's going to be y is a function of x. I'm not even going to draw any vertical lines. Hopefully you can see that there is no vertical line that can touch the graph in more than one place. The next chunk of problems, 11 through 18, I guess, give me equations that I may know how they graph. If I can get the graph of my equation, I can determine whether y is a function of x or not. There are algebraic ways to determine whether y is a function of x that I don't teach. This is not the most important topic, and I want to save some time here, so and not impact your success in higher math classes. So determine whether the equation represents y as a function of x. Hint, solve for y if necessary, then sketch a graph using your calculator. So for number 12, let me just sketch a graph. I should know from intermediate algebra or college algebra prep or high school math that this is a parabola that opens up, but you don't really have to. Turn my calculator on, hit my y equals button. Make sure none of these plots are on. If you have a plot on like that, if it's blacked out, arrow up to it, hit the enter key to shut it off. Clear anything out that's in there by hitting your clear button. Now use the X key, the squared key, and then +4. I have no idea what Windows setting in my calculator. If I hit the graph key right now, I might not see what I want to see. Safely for most of our graphs, if you just hit the zoom button and followed by number 6, that's going to be a safe enough window. I don't need to duplicate this graph on my paper. I just need to look at this graph and ask myself, Is it possible to draw a vertical line to touch that graph in more than one place? I don't think so. It looks like that's all the vertical lines would only touch in more than, they only would touch in one place. So this graph represents y is a function of x. Problem 14 gives me the square root of x minus 2. Let me go back to my y equals, clear out the function that's in there, activate the square root. The square root's on the x squared key, it's in blue. So to get the square root for x minus 2, I hit the second button, followed by the x squared key. That gives me the square root. It starts with a left parentheses, which means I need to end with a right parentheses. I'm going to use my x by the alpha key, minus by the plus sign to close my parentheses. Because I already have a nice window, I can just hit the graph button. I don't have to hit zoom standard every time. Just hit graph now that I have a nice window. And similarly, I don't see any way to draw a vertical line to touch that graph in more than one place. So for 14, I'm going to write the same answer. Y is a function of x. If he just says is a function, that's what my test key would say. I can live with that. These next problems, boy, maybe you know how to graph these from what we did on circles. Both of these graph to be circles. Problem 15, if I rewrote it, it would be y minus 0 squared plus x minus 0 squared. And if I square root 9 equals to 3 squared, if you know that that graph's to be a circle, then you don't have to do anything fancy on your calculator. Similarly, my 16, I can write as x minus 2 squared plus y minus 0 squared equals 4 squared. And I can graph this without my calculator. Hopefully you haven't forgotten circles so much that you can't graph this. And let me do that, because it's a heck of a lot easier to graph this by hand than it is on my calculator. So let me do a really crude graph. The center of this is going to be positive 2 and 0. Your center is going to be 0 and 0. I square rooted the 16 to get 4. The radius is going to be 4. And remember how we graphed circles? We would plot the center. There's my center of 2, 0. And then I'm going to go up 4, right 4, left 4, down 4, and draw a circle. That's what the graph should look like. I mean, something like that anyway. And this clearly fails the vertical line test. Almost any vertical line I would draw that's within where the graph is going to touch the graph in more than one place. So for this, y is not a function of x. That's using knowledge that I'm not supposed to forget, but you may have forgotten. In the next two problems, I can't use any knowledge that I have unless you had some awesome teacher in high school and you remember some stuff that you may have not remembered. So 17 and 18, 18 wants me to graph y squared equals x plus 2. Unfortunately, if I'm graphing on my calculator, the equation needs to be absolutely solved for y. It can't be solved for y squared. To get this solved for y, I have to do this. I have to square root plus or minus square root. If I'm trying to get rid of a square by square rooting, I need a plus or minus. And this is going to give me y equals plus or minus the square root of x plus 2. My calculator doesn't have a plus or minus key for graphing. So when I go to graph this, I'm going to have to enter two separate graphs. One's going to be y equals the square root of x plus 2, y1 equals the square root of x plus 2, and the other is going to be y2 equals the negative square root of x plus 2. There's the positive square root of x plus 2, there's the negative square root of x plus 2. On my calculator, hit my y equals, clear out what's in here, so clear that. I'm going to go first, second, and x squared, and then x plus 2, close out my parentheses, hit enter, use the negative in the bottom row of the calculator for the negative square root of x plus 2, then second in x squared, x plus 2, and now just hit enter, or hit graph should I say, and it'll draw the graph for me. It's going to be a parabola on its side, and that clearly fails the vertical line test, so here we're going to say y is not a function of x. Usually if you have a y squared, y is not a function of x. I can't even think of a time when there is a y squared in an equation that y would be a function of x, but there's one that I just can't think of. All right, now the next skill, important skill, 100% lifted from my college algebra prep class. Finding the domain and range from a graph that's continuous, meaning it's not broken into pieces, and the points are connected. So when we have a graph that looks something like the problems in 19 and 20, where some points are labeled but all the points are connected, I can't just write down the domain as the x coordinates and the range as the y coordinates. Eventually we're going to find the domain and range, and this would be absolutely wrong for number 20. This would be an incorrect domain, because any place on the graph where the graph exists, there's a point that would need to be included in the domain. Like right here, here's the point 0, -1. If I was going to write the domain, 0 would have to be in the domain. Similarly, here's the point 1, 2. 1 would have to be in my domain. So just writing a domain of the points that are listed is not right. When a graph has all the points connected, you can't just list the x values to write the domain. You can't just list the y values to write the range. There's a strategy that we have to use, and usually the domains and ranges, when we have graphs that are continuous, meaning they're unbroken graphs, usually I can write the domain with just 2 numbers, and I can describe the range with just 2 numbers, and those 2 numbers will represent an interval. So our answers for the domain and the range in this section are going to be written with round parentheses when they're appropriate, square brackets where appropriate, with a comma between the 2 numbers that I put in a parentheses. And so when we go to write the domain and the range, we need to figure out whether the square bracket is in the proper symbol or a round bracket is a proper symbol, and what numbers start the domain, what numbers end the domain, what numbers start and end the range. And this, I've typed up some stuff. Let me go through it a little bit here, because this is really important. So when I go to write my domain and range in this section, I'm going to use round parentheses for any point that's marked with an open circle, and if the number I need to put in is infinity or it's opposite of negative infinity. So if I'm about to write a domain or a range, and the point that I use to find the domain is marked with an open circle, that number is going to be preceded or followed if it's at the end of the bracket with a round parentheses. If I'm going to write an infinity or a negative infinity, that's also going to get a round parentheses. Square brackets I'm going to use when a point is marked with a closed circle, or if the point is an unmarked point on the graph, and we'll have some of all these coming up. So how do I find the domain and range when I'm given a graph? Not particularly hard to do. To find the domain if I'm given a graph, I identify the x coordinate of the most left point on the graph, place it after the appropriate symbol, either a round bracket or a square bracket, and then I identify the x coordinate of the most right point on the graph, place it before the appropriate symbol. Let me show you in terms of problem 20. Problem 20 is a lovely problem because it's a really simple graph. So for problem 20, if I was trying to find the domain for this, I know the domain is going to be in the form one number, comma, another number, and then I need to get the appropriate brackets or parentheses in. So what I need to do when I go to find my domain is identify the left edge of the graph and the right edge of the graph. So this point, negative 1, 6, negative 1, negative 6, this is the point that's furthest left on my graph. This point right here is going to be the start for my domain. My domain, I read from left to right. And I use x values. When I go to write the domain for problem 20, the number that's going to start with is negative 1. The kind of bracket that's going to precede it is a square bracket because this point is marked with a solid circle as opposed to an open circle. If that circle wasn't colored in with red and it was like that, I would put a round bracket. So I have the point that's furthest left on my graph for the start of my domain, and now the point that's furthest right on my graph for the end of my domain. So domain, I read from left to right, find the left edge of my graph, find its x-coordinate, find the right edge of the graph, find its x-coordinate. At the right edge of my domain, I'm going to need the number 4. And again, that point's marked with a solid circle, so I get a square bracket. That would be the domain part of number 20. Let's do the same with the range. How do I find the range from a graph of a continuous function and write my answer in interval notation? Well, first I identify the y-coordinate of the lowest point on the graph, place it after the appropriate symbol, either a round parentheses or a square bracket, depending on how it fits up here. And then I identify the y-coordinate of the highest point on the graph, place it before the appropriate symbol. So for the problem that we're doing here, to do the range, I need to find the bottom point on the graph and the top point on the graph. So I'm going to find the very bottom of my graph, and this is the very bottom of my graph, which is the start of my range. So domains, I'm thinking vertical and left to right. Range, I'm thinking horizontal and bottom to top. This right here is the top or the end of my range. So if I can identify the left edge and the right edge of a graph, then I can find the domain pretty easily when a graph is just at one continuous, unbroken graph. Similarly, if I could find the bottom and the top, I can also write the range pretty easily. So ranges are y's, domains are x's. The y-coordinate at the bottom of my graph is negative 6. That's how my range is going to start. Because the point is marked with a solid circle, I get a square bracket. The top of my graph is the point 2, 3. The number that goes at the end of my range is going to be the number 3. Again, it's marked with a solid circle, so I get a square bracket. That's the easiest kind of domain and range, where the graph is in its entirety presented to me. Unfortunately, there'll be times that we're given a graph and the portion of the graph that we're given isn't all of the graph that exists, meaning the graph extends beyond what we see. I don't know how well this shows up, so let me draw this graph a little bit bigger. In this example right here, I ask in this write-up to find the domain and range of this graph. Well, when a graph is written like I have this graph here, and one of the edges isn't marked with a period, that means even though the graph terminated because my paper doesn't go on forever, it's implied that this graph goes on forever. And so this graph needs to be extended in the direction that it's going. And always when I'm trying to find a domain or a range and I have to extend a graph, you're going to get infinities probably somewheres for a domain and a range. So this graph should be extended like this. So when I go to find the domain of this graph, I couldn't box it in. There isn't really a physical left and a physical right edge. There's absolutely a physical left edge. This right here is going to be my start for my domain. It's the very left edge of the graph. But it doesn't have a hard right edge. So when it doesn't have a hard right edge, the end of the domain is infinity. Because this graph right here, if I extend my x-axis, the far right edge of the x-axis is at infinity, and this graph will ultimately make it to the far right edge of the x-axis. I have no idea what this point is in terms of its y, but that doesn't matter. If I'm going to write the domain for this graph, I'm going to write the x-coordinate of the left edge of the graph, which is 2. Put the correct bracket between it. Because that point's marked with a solid dot, I put a square bracket before it. Make my comma, and then there isn't a right edge of the graph. When the graph goes forever to the right, the domain always ends with positive infinity. So that would be the second number that will go in my domain. And infinities always get round brackets. The two times we get round brackets are if points are marked with open circles or if I have an infinity. For the range for this, when a graph extends one of the pieces of the domain, or possibly both if it extends in both directions, and when the graph extends in one direction but not both directions, usually one of the parts of the domain is a number, the other is infinity. Similarly, when the graph extends in one direction, one of the part numbers in the range is an infinity, possibly negative infinity, and the other is a number. For the domain, for the range, it's real easy to see the top of this graph. So this right here, this is the top or the end of my range. When I'm going to write the range for this graph, I know I'm going to have a parentheses with two numbers in it, possibly some infinities. The end of my range is going to be at -1 for that y, and it's going to be square bracketed because that's physically a point on the graph marked with a closed circle. Unfortunately, this graph goes down forever. It goes right quicker than it goes down, but if a graph is decreasing or just going down as I move from left to right, we say that the bottom of the graph is at the bottom of the y-axis, which has a y-coordinate of infinity. So the bottom of the graph is going to have a y-coordinate of negative infinity because on the y-axis, the numbers beneath, as we go down are negative. So right here, this is going to be the start of the range. I don't really know what the point is. I don't really have an x and a y, but this graph goes down forever. And if I read from bottom to the top, this graph goes down all the way to the bottom of the y-axis, which has a y-coordinate of negative infinity. My range is going to start at negative infinity, end at the top -1, and infinities always get round brackets. So the appropriate range for this would be round parentheses, negative infinity, comma, -1, square bracket. Let's do problem 22 together. Getting close to where I should probably break this video, but I'll do a few more. So in problem 22, I have the left edge of the graph fixed. The right edge of the graph isn't labeled, so it needs to go like that. When I extend a half, that half is going to get infinities for the y and for the x. This half right here, the x is going to be positive infinity when I go to write my domain because it's going right. It's going to the right edge of the x-axis, which is positive infinity. So when I get the appropriate infinity in my domain, it's going to be positive infinity. And when I go to write my range in a minute here, well, this graph goes to the bottom of the y-axis. The number I'm going to put for the y is negative infinity, because this portion of the graph, it's going right in terms of the x direction, which is the positive x direction. It's going down in terms of the y direction. So now that I have that in my mind, I'm going to start to write the domain. For the start of my domain, I need the left edge. And the left edge goes through the point -1, 6. The number part of it is going to be -1, and it's going to be square bracketed because that point's marked with a solid circle. For the end of my domain, this is where the infinity is going to come in, because I go left to right. There isn't a right edge of the graph. I'm going to put an infinity in for the end of my domain. Infinities always get round brackets. So I read from left to right. The left edge was fixed, so it got the -1. The right edge is where my infinity came up with. For the range, I read the bottom from bottom to top. This graph has a real top, which that's going to be the end of my range. And that's going to be at y equal to 3. So when I go to write my range, 3 is going to end it because that's the top of it. There really isn't a bottom. The start of my range is at the very bottom of the graph, and the very bottom of the graph has a y of negative infinity. Infinities always get round brackets. So that would be the domain and the range. Let me do one more and then we'll break this video into a part 2. Even though there's not going to be anything new, it's just getting too long. Problem 24, I have to extend both directions. If I have to extend both directions, I could get 2 infinities in my answers. So this right here, I'm going to extend this, which extends for the x direction. It extends to in the left direction on the x-axis. So for my domain, for this extension, I'm going to need an x equal to negative infinity because it's going left, and in the x-axis, negative is left. And for this extension, it's going down. So for the range, I'm going to need a y equals negative infinity. This side also needs to be extended. And in terms of the x's, it's going right as it goes down. So for the x's, I'm going to need a positive infinity from this extension. But it's still going down. So for the range, I still need that same negative infinity. So I can see here that the range is only going to have one infinity because both extensions give me the same range. But the domain is going to have both infinities. When I go to write the domain for this, it's going to be from this negative infinity to that positive infinity. There isn't really a left edge. There isn't really a right edge. The left and right edges are non-existent because the graph keeps going to the right as it goes down and left as it goes down. Infinities always get round brackets. So here my domain is negative to positive infinity. For my range, I read from bottom to top. The bottom on both sides are y equals to negative infinity. Infinities always get round brackets. But this guy, I didn't ever extend it up. It has a hard top. And my end of my range is going to be this y equal to 3. And I'm going to square bracket that y equals to 3. All right, so we'll do a second part to this video just because it's way longer than I wanted this to be already. But there won't be anything new. Well, maybe there'll be some stuff new. Yes, there is, so it's worthy. There's finding domains and ranges when you're not having a graph that we need to worry about here in a bit.